What if everything you knew about the universe ended up being wrong? From the moment we wake up to the moment we fall asleep, we trust that the world around us is real. The ground beneath our feet feels solid, the sky stretches above us, and time moves forward. But modern physics is beginning to challenge these assumptions in ways we never imagined. Experiments in quantum mechanics suggest that reality might not be as stable or even as real as we've always believed. Some now wonder if the universe is an illusion, a vast cosmic trick of the light. Let's dive into the strange discoveries that make us question if the universe truly exists at all. The Einstein-Podolsky-Rosen paradox. Can the universe be local? The Einstein-Podolsky-Rosen paradox was a thought experiment proposed by Albert Einstein, Boris Podolsky, and Nathan Rosen in 1935. It challenged the strange implications of quantum mechanics, particularly its suggestion that particles could be connected in ways that seemed impossible under the rules of classical physics. At the heart of their argument was the question of whether the universe is local, meaning that objects are only influenced by things happening in their immediate surroundings, or if it might operate in a more mysterious way. In everyday life, we experience the world as local. If you push a chair across the room, it only moves because you physically touched it and applied force. Objects are not affected by distant things unless there's some form of connection, like a rope pulling one object toward another. This idea of locality feels natural to us because it fits with our experiences. Physical objects exist in space, and their properties and actions seem limited to their immediate environment. But the EPR paradox challenges this assumption by suggesting that particles could interact with each other in ways that defy local behavior. Einstein and his colleagues were troubled by the idea of quantum entanglement, where two particles, once connected, would remain linked regardless of distance. If you measured one particle's state, the other would instantly adjust its state, even if it was light years away. This seemed to suggest that information could travel faster than the speed of light, violating the very principles of relativity that Einstein himself had helped develop. It also raised the question of how two objects separated by such vast distances could be so closely intertwined. To Einstein, this idea was unacceptable. He famously referred to it as spooky action at a distance. The EPR paradox was designed to show that there must be something missing in our understanding of quantum mechanics. Einstein, Podolsky, and Rosen believed that the theory was incomplete. They thought there had to be hidden variables, unknown factors that would explain the seemingly impossible behavior of entangled particles. If we could discover these hidden variables, the mystery would disappear, and the universe would once again make sense as a place governed by local interactions. But quantum mechanics didn't offer any easy answers. According to the theory, entangled particles really do behave in ways that defy locality. When one particle is measured, the other instantaneously responds, no matter the distance. There's no obvious way to explain this behavior through hidden variables or local effects. This led to a deep divide in the scientific community. On one side were those who, like Einstein, believed that quantum mechanics was incomplete. On the other side were those who accepted that the universe might be far stranger than previously imagined, with non-local connections playing a fundamental role in the workings of reality. The EPR paradox remained unresolved for several decades, but it sparked a wave of interest and debate. It forced physicists to question the very foundations of their field and to grapple with the possibility that reality might not be as straightforward as they had believed. This shift in thinking was crucial for the development of modern physics. It paved the way for new theories and experiments that would further challenge classical views of the universe. One of the most important developments in this regard came with the work of physicist John Bell in the 1960s. Bell built on the EPR paradox to create what became known as Bell's theorem, a groundbreaking idea that put these questions to the test. Bell's theorem didn't rely on hypothetical thought experiments. Instead, it provided a framework for real-world experiments that could determine whether the universe was truly local, as Einstein had hoped, or whether it was governed by the strange, non-local rules of quantum mechanics. These experiments showed that there was no way to explain the behavior of entangled particles using local hidden variables. The results confirmed that the universe does not behave in a strictly local way. For Einstein, who passed away in 1955, this would have been a disappointing outcome. He had hoped that a deeper understanding of physics would restore the idea of a predictable, local universe. But Bell's theorem and the experiments that followed suggested otherwise. The universe seemed to be fundamentally interconnected in ways that classical physics could not explain. This finding turned the EPR paradox from a challenge to quantum mechanics into a key piece of evidence supporting it. The universe as a mirage, questioning reality's bedrock. The way we experience the universe is grounded in our senses. We trust that what we see, hear, and feel is real. A tree we touch feels solid, the sky looks blue, and gravity pulls us down toward the ground. All of these experiences create a world that seems stable and predictable. But what if reality isn't as concrete as it seems? What if the world we experience is just a mirage shaped by our minds? For centuries, philosophers have questioned the nature of reality. One of the oldest debates is whether the world exists independently of our perception or if it is shaped entirely by how we experience it. Thinkers like Plato imagined that the world we see is only a shadow of a deeper, truer reality. Others have suggested that everything we know might just be a construct of the mind. What we call reality could be nothing more than an illusion, a projection that seems stable only because we need it to be. Modern science has added new layers to this age-old debate. Quantum mechanics, in particular, has thrown many of our classical ideas about the universe into doubt. In the world of the very small, things don't behave as we expect. Particles can be in more than one place at the same time. Objects can affect each other instantaneously, even when separated by vast distances. And some things only seem to exist when we observe them. This strange behavior has led to serious questions about the nature of reality itself. Our everyday experience suggests that the universe follows clear rules. Drop a glass and it will shatter. Walk across a room and you'll move from one point to another. But quantum mechanics reveals that these rules may not apply at the fundamental level. In fact, particles that make up everything around us behave in ways that are completely foreign to our normal understanding. For example, they don't have a definite location until they're observed. This phenomenon is known as superposition. Before we measure or observe a particle, it exists in a kind of probability cloud, where it can be in multiple states at once. Only when we look does it choose a state. If the universe only takes shape when we observe it, can we still say that it exists independently of us? Is reality something that's out there, fixed and stable, or is it fluid and constantly changing based on how we interact with it? This also leads to questions about the role of the observer. Quantum mechanics seems to suggest that we, as observers, play a crucial role in shaping the universe. The famous thought experiment of Schrödinger's cat illustrates this well. In this scenario, a cat is placed in a box with a device that has a 50-50 chance of killing it. Until someone opens the box and observes the cat, it is said to be both alive and dead at the same time. The cat's fate only becomes real when an observer looks inside the box. This thought experiment is meant to show how strange and counterintuitive quantum mechanics can be. It also suggests that reality might depend on whether or not we are observing it. This line of thinking aligns with some philosophical traditions, especially in Eastern philosophy. For example, in Buddhism, the idea of Maya refers to the illusory nature of the world. It suggests that what we perceive as reality is not the ultimate truth, but a kind of veil that hides deeper, more fundamental truths. In a similar way, modern physics might be revealing that the universe we experience is a kind of veil, masking a more complex and less intuitive reality beneath it. One of the most striking examples of how quantum mechanics challenges our understanding of reality is the concept of entanglement. When two particles become entangled, they remain connected no matter how far apart they are. If you change the state of one particle, the other particle's state changes instantly. even if it's on the other side of the universe. This seems to defy our understanding of space and time, suggesting that distance and separation might be illusions at a fundamental level. Bell's theorem, shattering classical assumptions of reality. Bell's theorem took the puzzling implications of the EPR paradox and turned them into something testable. Before Bell, the debate about quantum mechanics had largely been theoretical. The EPR paradox raised serious questions about whether the universe was truly governed by local interactions, but there wasn't a clear way to test the idea in a practical setting. Bell changed that by showing how we could determine whether the strange world of quantum mechanics really defied classical ideas of locality. Bell's theorem was a groundbreaking step forward because it didn't just ask whether hidden variables might exist. It outlined a series of mathematical inequalities, known as Bell inequalities, that could be used to test whether these variables could preserve the principle of locality. If quantum mechanics was right, experiments would violate Bell's inequalities. If Einstein was right, the inequalities would hold, meaning that some hidden variables must be at play to explain the results. Scientists began conducting these experiments in the 1970s and 1980s. The first major experimental test of Bell's inequalities came in 1972, led by physicists John Clauser and Stuart Friedman. Their work was groundbreaking because it was the first real attempt to measure whether entangled particles truly behaved in a way that couldn't be explained by local hidden variables. Another important breakthrough experiment came in 1982 by Alain Aspect and his team in France. The results were clear. The Bell inequalities were violated, meaning that there were no local hidden variables to explain the behavior of entangled particles. Particles separated by great distances could influence each other instantaneously, as if space and time themselves did not apply at the quantum level. Bell's theorem showed that quantum entanglement wasn't just an odd quirk of the theory. It was a fundamental aspect of how the universe works. The behavior of entangled particles couldn't be explained by any classical means, meaning that quantum mechanics was indeed pointing to a reality that defied our everyday experiences. One of the most exciting consequences of Bell's theorem is the way it opens up new possibilities for technology. Quantum entanglement, once seen as a strange curiosity, has now become a key area of research for developing technologies like quantum computing and quantum cryptography. In quantum computing, entangled particles can process information in ways that classical computers simply can't match. The instantaneous connection between entangled particles can be used to solve complex problems far faster than traditional methods allow. Similarly, in quantum cryptography, the strange properties of entanglement offer new ways to secure communications, as any attempt to eavesdrop on an entangled system would immediately disturb the particles, alerting the intended recipient to the breach. Because entangled particles can share information instantly, it suggests that information might not be tied to physical objects in the way we're used to thinking. Some physicists even speculate that information is a fundamental building block of the universe, more fundamental than matter or energy. What is quantum entanglement really telling us? Quantum entanglement has become one of the most puzzling and fascinating aspects of modern physics. To grasp the significance of quantum entanglement, we need to step back and consider what it's telling us about reality. In classical physics, events are separated by time and space, and the cause and effect relationship between them follows clear rules. For example, if you throw a stone into a pond, the ripples spread outward from where the stone entered the water. You can trace back the effect, the ripples, to a specific cause, the stone. There's a clear connection between cause and effect, and it's bound by the laws of space and time. But quantum entanglement throws this clear connection into question. Imagine you have two entangled particles, one on Earth and the other on the opposite side of the galaxy. If you measure the state of the particle on Earth, the state of the distant particle will instantly adjust to match the outcome of that measurement, even though there has been no time for information to travel between them. This instant connection, doesn't seem to follow the rules of space and time that govern the classical world. Instead, it suggests that the two particles are linked in a deeper, more fundamental way, as if they are part of the same system regardless of the distance between them. One of the first things entanglement challenges is our understanding of causality. In the classical world, causes lead to effects, and those effects follow the cause in a logical sequence. But in the quantum world, entangled particles don't seem to follow this sequence. The outcome of a measurement on one particle immediately influences the state of the other, without any apparent cause and effect relationship between them. This raises the possibility that the universe at its most fundamental level may not operate according to the strict cause and effect rules we observe in our everyday lives. Some physicists have suggested that entanglement points to a reality where time and space are not as fixed or fundamental as we once thought. In this view, the entangled particles aren't communicating with each other faster than light. Instead, the concept of distance between them is meaningless. The particles are part of the same system, and their separation is an illusion created by our limited understanding of space and time. From this perspective, quantum entanglement might be telling us that the boundaries we perceive between objects, events, and even time itself are not as real as they seem. This idea can be difficult to grasp because it challenges so much of what we take for granted about the world. We live in a universe where objects appear to be separate and distinct from each other. A tree is not the same as a rock, and a person on the other side of the planet isn't directly connected to you. But quantum entanglement suggests that this separateness might be an illusion at a deeper level of reality. If particles can remain connected across vast distances, then maybe the universe is more interconnected than we realize, with unseen links that go beyond our usual understanding of space. Another way to think about this is to consider that reality might not be made up of individual objects at all, but rather of relationships. In classical physics, we think of the universe as a collection of independent objects, each with its own properties, moving through space and time. But in the quantum world, it seems that these objects can't be fully understood in isolation. Their properties only make sense in relation to other objects, particularly when they are entangled. This suggests that the fundamental building blocks of reality might not be things, but the relationships between things. We tend to think of ourselves as distinct individuals, separate from the world around us. But if everything is fundamentally interconnected, then the boundaries between self and other might not be as clear as we think. This has led some philosophers to suggest that quantum entanglement could provide a new way of thinking about consciousness and existence. If particles are connected across space, could consciousness itself be part of this interconnected fabric? One of the most puzzling aspects of entanglement is how it relates to information. It has led some physicists to wonder whether information itself might be the most fundamental building block of reality, rather than matter or energy. Some theories suggest that the universe might be built not from physical objects, but from information, with entanglement being one way that this information is shared across the universe. If this is true, it would further blur the line between the physical and non-physical aspects of reality. Information, unlike physical objects, isn't bound by the same rules of space and time. It can exist in many forms. An entanglement might be a glimpse into how information operates at the most fundamental level of the universe. Entanglement also calls into question the role of the observer in shaping reality. In classical physics, the properties of an object exist independently of whether or not we observe them. But in quantum mechanics, it seems that the act of observation plays a crucial role in determining the state of an entangled particle. Before measurement, the particle exists in a state of superposition where its properties are not fixed. Only after interaction with the particle does its properties collapse into a definite state. Beyond Einstein, how quantum mechanics defies space-time. Quantum mechanics and Einstein's theory of relativity, particularly general relativity, are two pillars of modern physics. but they describe the universe in very different ways. Einstein's theory gives us a picture of a smooth, continuous fabric of space and time, known as space-time, that governs the behavior of massive objects like stars and planets. In this view, space-time bends around objects with mass, and this bending is what we perceive as gravity. Relativity is incredibly successful at explaining the large-scale structure of the universe, from the orbits of planets to the motion of galaxies. But quantum mechanics, which deals with the tiniest particles in the universe, tells a completely different story, one that challenges our understanding of space and time itself. One of the key differences between these two theories lies in how they treat space and time. In Einstein's theory, space-time is a continuous fabric, meaning that it can be stretched and warped, but it doesn't have any gaps or breaks. Objects move smoothly through space-time, and the passage of time is affected by things like speed and gravity. For example, time moves more slowly for someone traveling near the speed of light, or for someone standing near a massive object like a black hole. This is called time dilation, and it's a key prediction of general relativity that has been confirmed by many experiments. But quantum mechanics paints a very different picture. In the quantum world, space and time don't behave in the smooth, continuous way that relativity suggests. Instead, at the smallest scales, space and time seem to break down into discrete, almost pixelated units. In this strange world, particles can pop in and out of existence, and they don't move in smooth paths through space. Instead, they jump from one location to another in what's called quantum tunneling. This behavior is completely at odds with the smooth, predictable nature of space-time in general relativity. One of the biggest challenges in modern physics is figuring out how to reconcile these two pictures of the universe. One of the most famous examples of this tension is the problem of black holes. According to general relativity, black holes are regions of space where the gravitational pull is so strong that not even light can escape. At the center of a black hole is a point called a singularity, where space and time are thought to break down entirely. But quantum mechanics tells us that this picture can't be complete. In the quantum world, information can't be destroyed, but general relativity suggests that anything falling into a black hole, including information, is lost forever. This leads to what physicists call the black hole information paradox, a clash between the rules of quantum mechanics and the predictions of general relativity. The strange behavior of quantum particles, like quantum entanglement and tunneling, also defies the classical understanding of space-time. As we've seen with entangled particles, they can influence each other instantly, no matter how far apart they are. This seems to violate the basic principle of relativity, which says that nothing can travel faster than the speed of light. In relativity, the idea of locality is fundamental. Objects in one location can't influence objects in another location unless some signal or force travels between them, and that signal can't go faster than light. But in quantum mechanics, this principle doesn't hold. Entangled particles behave as if they are part of the same system, no matter how far apart they are in space. In quantum mechanics, time also doesn't flow in the smooth, continuous way that we experience it in everyday life. Instead, at the smallest scales, time seems to behave more like a series of discrete moments. Some physicists believe that at the quantum level, time itself might be quantized, meaning it comes in tiny, indivisible units, much like energy in quantum mechanics. This is very different from the view in relativity, where time is a continuous dimension, flowing smoothly like a river. Physicists have been trying to resolve this tension between quantum mechanics and relativity for decades. But so far, a complete theory that unites the two has remained elusive. One of the leading candidates is string theory, which suggests that all the particles and forces in the universe are made up of tiny, vibrating strings. In string theory, space and time are not fundamental. They emerge from the vibrations of these strings at a deeper level. Another approach is loop quantum gravity, which suggests that space and time are made up of tiny loops, and that at the quantum level, the fabric of space-time is granular, not smooth. If space and time are not fundamental, but instead emerge from the quantum world, then the universe we experience is only one layer of a much more complex reality. The classical, predictable world of space-time is built on top of a chaotic, uncertain quantum world, where the usual rules of cause and effect, space and distance, and even time itself break down. The Nobel winners of 2022, proving reality's strangeness. In 2022, the Nobel Prize in Physics was awarded to 3 scientists: Alain Aspect, John Clauser, and Anton Zeilinger, whose experiments were instrumental in proving the violation of Bell inequalities. The experiments conducted by Clauser, Aspect, and Zeilinger did more than just confirm the strange predictions of quantum mechanics. They fundamentally changed the way we understand the universe. By proving the violation of Bell's inequalities, they showed that the classical idea of a local, objective reality, where objects have definite properties and only influence each other through local interactions, is not how the universe works. Their experiments not only confirm the strange predictions of quantum mechanics, but also hint at deeper, unresolved questions about the nature of reality. If space and time are not as fundamental as we once thought, what lies beyond them? How do we reconcile the smooth, continuous fabric of space-time in general relativity with the strange, non-local behavior of particles in quantum mechanics? These are questions that physicists are still grappling with today, and the work of Clauser, Aspect, and Zeilinger has provided crucial clues for exploring these mysteries. In many ways, the 2022 Nobel Prize in Physics recognizes not just the achievements of these 3 scientists, but also the broader shift in our understanding of the universe that their work represents. Quantum mechanics has always been a strange and counterintuitive theory, challenging our basic assumptions about reality. But the experiments conducted by Clauser, Aspect, and Zeilinger showed that this strangeness was not just a theoretical curiosity, but a fundamental feature of the universe we live in. John Clauser's work, Unveiling a Quantum World Without Hidden Variables. John Clauser's work in the 1970s was a turning point in the experimental verification of quantum mechanics. At a time when the strange predictions of quantum theory were still met with skepticism, Clauser's experiments offered some of the first direct evidence that the universe might indeed operate in a way that defies classical notions of space, time, and causality. What Clauser managed to do was to bring these abstract ideas into the lab, conducting experiments that could either confirm or refute the core predictions of quantum theory. At the heart of this debate was the idea of local hidden variables. In classical physics, it was generally assumed that objects had definite properties: position, momentum, energy, whether we measured them or not. This idea is often referred to as realism, the belief that the physical world exists independently of observation. When quantum mechanics emerged in the early 20th century, it challenged this assumption by suggesting that, at the microscopic level, particles could exist in a superposition of states. They could be in multiple places or have multiple properties at once, and only when they were observed would they collapse into one state. This deeply unsettled many physicists, including Albert Einstein, who famously argued that God does not play dice with the universe. Einstein believed there must be hidden variables, factors we couldn't see or measure, that determined the seemingly random behavior of quantum particles. Bell's theorem, proposed in 1964, offered a way to test this idea of hidden variables. Bell formulated a mathematical inequality, now known as Bell's inequality, which provided a way to determine whether or not hidden variables could be at work. Clauser took up the challenge of testing Bell's inequality in the lab. Working with Stuart Friedman, Clauser set up an experiment in which pairs of entangled photons were emitted from a single source and sent in opposite directions to 2 detectors. According to quantum mechanics, if the 2 photons were entangled, the measurement of one photon's state would instantly determine the state of the other photon, no matter how far apart they were. In classical physics, this would seem impossible. no signal could travel faster than the speed of light. So how could two particles that were light years apart influence each other instantaneously? Clauser's experiment was one of the first to directly test this prediction. By measuring the polarization of the two photons and comparing the results, Clauser and Friedman were able to calculate whether the outcomes violated Bell's inequality. The results demonstrated that the photons did, in fact, violate Bell's inequality. This meant that the behavior of the entangled photons could not be explained by any local hidden variables. In other words, there was no classical mechanism that could account for the correlations between the two particles. Instead, the results pointed to the conclusion that quantum mechanics was correct and that entanglement was real. Clauser's work provided experimental evidence for something that had previously been dismissed as merely a mathematical curiosity. Quantum entanglement, which Einstein had referred to as spooky action at a distance, was not just a theoretical oddity. It was a real phenomenon that could be measured and tested. His experiments also had broader implications for the nature of reality itself. If there were no hidden variables, then the behavior of quantum particles was not determined by any underlying classical laws. Instead, the outcomes of measurements were genuinely random, governed only by the probabilities predicted by quantum mechanics. This led to a profound shift in how physicists understood the nature of the universe. In classical physics, the universe was seen as a deterministic system, where the past determined the present and the present determined the future. But in the quantum world, randomness and uncertainty were fundamental aspects of reality. Moreover, Clauser's work raised important questions about the role of the observer in quantum mechanics. In the classical view, measurements were simply a way of revealing the pre-existing properties of objects. But in the quantum world, observation played a more active role. According to the theory, the act of measurement caused the collapse of the wave function, bringing the particle into a definite state. This suggested that reality, at least at the quantum level, was not something that existed independently of observation. Instead, the observer played a crucial role in shaping the outcomes of measurements. Alain Aspect's experiments, closing the loopholes in Bell tests. Alain Aspect's experiments in the 1980s further strengthened the case for quantum non-locality. His work wasn't just about replicating previous tests of Bell's theorem, it was about refining those tests in a way that eliminated potential loopholes and doubts. By doing this, Aspect and his team helped to cement the idea that the behavior of entangled particles was not something that could be explained away by hidden variables or communication between the particles at speeds faster than light. Earlier experiments, like those conducted by Clauser, had already provided strong evidence in favor of quantum mechanics. However, Clauser's results left open some possibilities for skeptics to argue that hidden factors might still be influencing the outcomes of the experiments. These were referred to as loopholes in the tests. One of the major loopholes that Alain Aspect addressed in his experiments was the locality loophole. In Clauser's experiment, for instance, the detectors used to measure the entangled particles' properties were set before the particles were emitted. This raised the question of whether the particles somehow knew what settings the detectors were using, allowing them to coordinate their behavior in a way that mimicked the effects of quantum entanglement. If the particles could exchange information during the experiment, even at faster than light speeds, this would suggest that the results weren't purely a consequence of quantum mechanics, but could instead be explained by hidden communication between the particles. Aspect's experiment dealt with this problem by making the crucial step of altering the settings on the detectors while the particles were in flight. Instead of setting the detector parameters in advance, Aspect introduced a random element into the experiment by changing the settings only after the particles had already been emitted and were on their way to the detectors. This eliminated the possibility that the particles could have known in advance what the settings would be, thus closing the locality loophole. His results showed that even with the randomized detector settings, the particles continued to violate Bell's inequalities, providing strong evidence that quantum mechanics was correct, and that no local hidden variables or faster-than-light communication was at play. The technical achievement of Aspect's work was significant. Changing the detector settings mid-flight was no small feat. It required precision timing and advanced technology. The particles, often photons or light particles, travel at incredibly high speeds. Altering the settings of the detectors in the brief moment while the particles are moving between the source and the detectors required a level of synchronization that had never been attempted in such experiments before. Yet, Aspect's team was able to implement this change successfully, proving that the experimental design was sound and reducing the chances that any hidden communication could explain the results. With the locality loophole effectively sealed, it became much harder for skeptics to argue that the results of these experiments could be explained by classical physics or some as yet undiscovered force. But Aspect's work didn't stop there. He also tackled another significant problem in these types of experiments: the detection loophole. This loophole arises when not all of the particles being measured are detected during the experiment. In earlier tests, the detectors didn't always catch every photon, and some of the particles would escape without being measured. This left open the possibility that the particles that were detected behaved in a way that violated Bell's inequalities, while the ones that weren't detected might have followed the rules of classical physics. If this were the case, it would suggest that the results were biased by the fact that only certain particles were being measured. Thus, Aspect also improved the efficiency of his detectors to reduce the number of undetected particles. By ensuring that a higher percentage of the photons were actually measured, Aspect's experiments made it less likely that the results were skewed by only measuring certain particles. As with the locality loophole, the results still showed violations of Bell's inequalities, suggesting that quantum non-locality was indeed a fundamental feature of the universe. The more loopholes that were closed, the stronger the evidence became for quantum mechanics, and the more the classical understanding of the universe was challenged. By addressing the loopholes that had cast doubt on previous experiments, Aspect's work provided a much firmer foundation for the idea that quantum entanglement was real and that the universe didn't operate according to classical local rules. Anton Zeilinger and quantum teleportation, probing the edge of reality. The experiments conducted by Clauser and Aspect provided definitive proof of quantum entanglement, confirming the strange non-local behavior of particles. Building on this solid foundation, Anton Zeilinger took the next logical step. He asked, if particles could be entangled and share information instantaneously, could this principle be used to teleport information from one particle to another without any direct physical contact? The answer was yes, and this concept became known as quantum teleportation. While teleportation in the classical sense, the instantaneous movement of objects, remains the stuff of science fiction, what Zeilinger accomplished was profound in a different way. He and his team demonstrated the ability to transfer the quantum state of a particle from one location to another, using entanglement as the conduit for that transfer. This was no small feat and required intricate setups involving lasers, photons, and measuring devices capable of detecting quantum states with great precision. Zeilinger's experiments often involved entangling photons, particles of light, as they are easier to manipulate than heavier particles. In a typical quantum teleportation experiment, 3 particles are involved: 2 entangled particles, A and B, and a third particle, C, which is the one whose state is to be teleported. First, particle C interacts with particle A, causing A's state to change. Because A is entangled with B, this interaction causes B to take on a state related to C's state, even though C and B never interacted directly. In this way, the quantum information about particle C is transferred to particle B, effectively teleporting C's quantum state. What's critical to understand is that the physical matter of particle C doesn't move. Only the information about its quantum state does. This is what makes quantum teleportation different from the teleportation we imagine from movies and books. In quantum teleportation, it's not about moving an object from one place to another, but about transferring the information that defines the object's quantum properties. This might seem abstract, but it has profound implications for how we understand the universe. Zeilinger's work showed that, at the quantum level, information might be more fundamental than the particles themselves. Zeilinger's experiments also built on the concept of the no-cloning theorem, a rule in quantum mechanics that states that it's impossible to make an exact copy of an arbitrary unknown quantum state. Quantum teleportation doesn't violate this rule because the original state, in a sense, ceases to exist in its original form once it has been teleported. This subtle but crucial detail underscores how deeply quantum mechanics diverges from classical intuition. In classical physics, copying information or objects is straightforward, but in the quantum world, the rules are entirely different. Zeilinger's teleportation experiments played within these strange quantum laws, demonstrating that even though we can't make a perfect copy of a quantum state, we can still transmit it across space instantaneously using entanglement. In one of his later experiments, conducted in 2012, Zeilinger and his team successfully teleported the quantum state of a photon over a distance of over 143 kilometers between two Canary Islands. This experiment was groundbreaking because it showed that quantum teleportation wasn't just a theoretical possibility. It could be done in practice over significant distances. The experiment also reinforced the idea that entanglement is real and robust, even when the entangled particles are separated by a large distance. This result was an important step toward future technologies like quantum communication and quantum networks, which could revolutionize how we transmit information, making it far faster and more secure than traditional methods. His experiments showed that information could be transferred in a fundamentally different way than anything we experience in the macroscopic world. It raised the possibility that information, rather than being just a property of physical systems, might be something even more fundamental. In fact, some physicists began to speculate that information might be the most basic building block of the universe, more fundamental than particles or energy. According to this view, reality itself could be seen as a vast web of information, with physical objects and particles merely manifestations of this underlying structure. What does it mean to violate Bell inequalities? The violation of Bell inequalities stands as one of the most profound results in modern physics. It forces us to rethink our understanding of the universe, raising questions about the very nature of reality. In experiments that tested Bell's theorem, when measurements were made on entangled particles, the results showed a level of correlation that could not be explained by any local hidden variable theory. The only conclusion was that either locality, the idea that objects are only affected by their nearby environment, was wrong, or the universe works in a way that is even stranger than we can imagine. One way to think about the violation of Bell inequalities is to compare it to flipping two coins. If you flip two coins that are physically separate, their outcomes should be independent. Sometimes both coins will land heads, sometimes both tails, and sometimes one heads and one tails. Over time, you'd expect to see a certain distribution of outcomes. But imagine a situation where every time you flipped one coin, the other coin instantly reflected the same result, no matter how far apart they were. This would suggest that the two coins are somehow connected in a way that defies the laws of classical physics. This is similar to what physicists found when they measured the behavior of entangled particles. The outcomes were more correlated than they should have been if each particle was acting independently based on local information. The violation of Bell inequalities doesn't just challenge the idea of locality. It supports the idea that reality, at its most fundamental level, may not be made of solid, stable objects, but rather of probabilities and relationships between particles. These particles only seem to choose their states when they are observed, and until that moment, their properties remain in a kind of limbo. This leads to one of the most unsettling implications of the violation of Bell inequalities. The universe may not be as real as we think. If particles don't have definite properties until they're observed, then what is the universe like when no one is looking? Does the moon exist when no one is observing it, or does it only snap into existence when it's measured? These questions, which might seem like the stuff of philosophy, are raised by real experimental data. The violation of Bell inequalities forces us to confront the possibility that the act of observation is not just a passive process of gathering information, but an active process that helps to create reality itself. At the heart of these ideas is the concept of non-locality. In classical physics, events that happen in one place can't instantly affect things far away. This idea is rooted in the notion that nothing can travel faster than the speed of light, as Einstein's theory of relativity tells us. But the violation of Bell inequalities suggests that, at the quantum level, this limit doesn't hold. Entangled particles seem to communicate with each other instantaneously, regardless of the distance between them. This isn't communication in the classical sense. No signal is being sent from one particle to the other. But the correlation between the two particles' states is undeniable, and it happens faster than light could travel between them. This is what physicists mean when they say that quantum mechanics is non-local. Events in one place can have instantaneous effects in another, without any physical connection between the two. Is the universe non-local, or does it not exist? The violation of Bell inequalities presents us with two potential ways to understand the nature of reality, both of which challenge our everyday experiences and the foundations of classical physics. Either the universe is deeply non-local, meaning that events in one place can instantaneously affect events far away, or the universe doesn't exist in the way we think it does. Both options seem to stretch the limits of what we find intuitively acceptable. But they are the inevitable conclusions drawn from decades of experimental results in quantum mechanics. If we take the idea of non-locality seriously, then the universe is connected in ways that defy classical understanding. This means that the fabric of space and time, which seems so solid and orderly on human scales, might not apply at the quantum level. Instead of objects being separated by distances and moving through time in a linear fashion, quantum mechanics suggests that particles can be linked across vast distances, interacting as if the space between them doesn't matter. Non-locality implies that information or influence can be shared between particles faster than the speed of light. In classical physics, Einstein's theory of relativity sets an absolute speed limit, the speed of light in a vacuum. Nothing is supposed to be able to exceed this limit, but quantum entanglement doesn't follow this rule. This doesn't mean that information is being transmitted faster than light, at least not in a way that we can harness or observe directly. But it does mean that our intuitive view of space and time doesn't fully apply at the quantum level. One possible interpretation of this is that the universe is interconnected on a fundamental level in ways that we don't yet understand. Perhaps space and time are not the basic building blocks of reality, but emergent properties that arise from something deeper. In this view, the universe is not made of individual objects moving through space, but of relationships and interactions between particles, and these relationships extend across what we think of as distances. This would mean that locality, the idea that objects only affect their immediate surroundings, simply doesn't apply at the quantum level. Another way to think about non-locality is to imagine that space itself is an illusion, or at least not fundamental. What we perceive as distance might be more like a side effect of how our brains interpret information, rather than a true property of the universe. In this interpretation, the reason particles can be correlated at a distance is that, at a fundamental level, they are not actually separated by space at all. Space is something that emerges from the underlying quantum reality, but it doesn't exist in the way we usually think of it. The other, perhaps even more unsettling possibility, is that the universe doesn't exist in the way we traditionally understand it. Quantum mechanics has led some physicists and philosophers to question whether reality is objective or whether it depends on observation. In classical physics, we assume that objects have definite properties, but quantum mechanics suggests that particles don't have definite properties until they are measured. Until a particle's state is observed, it exists in a kind of limbo, a superposition of all possible states. If particles don't have definite properties until they are observed, then does the universe exist in the same way when no one is looking? This idea, sometimes referred to as observer-dependent reality, suggests that the act of observation might be necessary for the universe to take on definite properties. In this view, reality is not something that exists independently of us, but something that is co-created through the process of observation. This doesn't necessarily mean that the universe ceases to exist when we aren't looking, but it does challenge the classical idea that the universe is an objective, stable thing that exists independently of us. Instead, it suggests that reality might be more fluid and dependent on interactions between particles and possibly observers than we ever imagined. Some interpretations of quantum mechanics, like the Copenhagen interpretation, lean toward this view, suggesting that particles don't choose a definite state until they are observed, and until that moment, reality remains indeterminate. There are other interpretations of quantum mechanics that try to avoid the idea of observer-dependent reality, but none of them fully resolve the paradoxes raised by quantum entanglement and non-locality. For example, the many-worlds interpretation suggests that all possible outcomes of a quantum measurement actually occur, but in separate parallel universes. In this view, when we observe a particle, we aren't causing it to choose a state, but are instead finding ourselves in one of many possible realities. Each time a quantum event occurs, the universe splits into multiple branches, each corresponding to a different outcome. The many-worlds interpretation avoids the problem of observer-dependent reality, but at the cost of introducing an infinite number of parallel universes. It suggests that the universe we experience is just one of many, and that all possible realities exist simultaneously. While this might seem like a strange idea, it is one way to reconcile the weirdness of quantum mechanics with the classical notion of objective reality. Another interpretation that seeks to preserve the idea of an objective reality is Bohmian mechanics, also known as pilot wave theory. In this interpretation, particles do have definite properties at all times, but they are guided by a pilot wave that determines their behavior. This wave is non-local, meaning it can influence particles across vast distances instantaneously, but it allows for a deterministic universe where particles have fixed trajectories. Bohmian mechanics restores some of the certainty and predictability that classical physics offers, but at the cost of accepting a non-local hidden wave that we cannot directly observe. Schrödinger's cat, a universe in infinite states. The Schrödinger's cat thought experiment is widely known as a paradox that illustrates one of the most bizarre aspects of quantum mechanics. At its core, the thought experiment forces us to confront the idea that, in the quantum world, an object can exist in multiple states at once until it is observed. While the image of a cat being both alive and dead simultaneously might seem more like a philosophical riddle than a physical reality, it serves as a doorway to deeper questions about the nature of existence itself. In the quantum realm, particles behave in ways that are fundamentally different from how objects in the classical world behave. Schrödinger's cat is a way of translating this strange behavior to a larger, more relatable scale, where we imagine an entire living organism, such as a cat, trapped in a quantum superposition. Inside the box, without anyone observing it, the cat is both alive and dead, living in two realities simultaneously. If this is true at the level of particles, what are the implications when we extend this idea to the universe? In quantum mechanics, the idea that something can exist in multiple states simultaneously isn't limited to single particles. It applies to any quantum system, no matter how large or complex. Some physicists have even suggested that the entire universe might exist in a superposition of states. This is an unsettling thought. It raises the possibility that the universe we experience might be just one version of countless others, with all possibilities existing at once. The universe as we know it may be just one outcome that we observe, while other universes, governed by different outcomes of quantum events, could exist alongside it, unobserved. According to this multiverse theory, if particles, and by extension the universe, can exist in multiple states at once, then every possible outcome of a quantum event could give rise to a different universe. In one universe, Schrödinger's cat is alive. In another, it's dead. In one universe, a particle goes through one slit. In another, it goes through both. And in each case, the different realities coexist, each as real as the other. The only thing that separates them is our act of observation. We only experience one version of reality, but the others may be just as real, hidden from us because we don't observe them. The multiverse theory is a radical idea, but it flows naturally from the principles of quantum mechanics. If quantum superposition is a real feature of the universe, then every quantum event could potentially give rise to a different version of reality. In this view, the universe isn't a single coherent entity, but a branching tree of possibilities, with every observation creating a new branch. Our experience of reality is just one path among many, a single thread in a vast, complex web of potential universes. This brings us back to the question of existence. What does it mean for something to exist if it can exist in multiple states at once? If the universe itself is in a superposition of states, then the very concept of existence becomes slippery. Are all the different versions of the universe equally real, or is there something special about the one we observe? And if our observations are what collapse the superposition and bring one version of reality into being, then does reality itself depend on us? Could it be that the universe doesn't exist in a fixed, stable state, but instead flickers between different possibilities, only becoming real when we look at it? Parallel universes, or non-existent ones. What's the difference? Since its inception, the idea of parallel universes has captivated human imagination, offering a mind-bending view of reality that is difficult to fully grasp. At its core, the many worlds interpretation of quantum mechanics suggests that every possible outcome of a quantum event spawns a new universe. These universes exist side by side, each representing a different version of reality. In this interpretation, when you make a decision, for example, whether to go left or right, the universe branches into two. In one version, you go left, and in another, you go right. Both outcomes exist simultaneously, but in different realities. This interpretation provides an elegant solution to the mystery of quantum superposition, where particles seem to exist in multiple states at once. According to the many worlds view, all these states are real, just not in the same universe. Instead, each possibility plays out in its own universe, leading to an endless proliferation of worlds, each slightly different from the others. In this picture, our universe is just one of many, a single thread in an infinite multiverse. But how do we reconcile this idea with the possibility that none of these universes, including ours, might truly exist? Some interpretations of quantum mechanics, particularly those influenced by philosophy, raise the unsettling possibility that reality itself might be an illusion. From this perspective, what we experience as reality could be nothing more than a projection of our minds, or worse, a kind of mirage created by the act of observation. In this view, there is no real universe out there, just a collection of appearances that arise when we interact with the quantum world. Are parallel universes more plausible than the idea that none of them, including our own, exist at all? Both ideas challenge our intuitive understanding of reality, but in different ways. The many worlds interpretation suggests that reality is much bigger than we can imagine, filled with countless universes that we can never access or observe. It implies that every possibility is real, but in a different universe. On the other hand, the idea that reality is an illusion suggests that none of these possibilities are real in any meaningful sense. What we think of as reality is just a shadow, a construct of our minds or our observations. The many worlds interpretation offers a kind of reassuring complexity. It suggests that while reality is stranger than we thought, it still operates according to some set of rules. The universes in the multiverse follow the same physical laws as our own, even if they play out differently. Each universe is as real as the next, and all of them exist independently of us. In this view, our actions might seem small in the grand scheme of things, but they are part of a much larger tapestry of existence. The universe we experience is just one thread in a cosmic fabric, woven from all the possible outcomes of quantum events. The idea that reality is an illusion is more unsettling. It suggests that the universe we experience might not be real at all, or at least not in the way we typically think of reality. If the universe is a kind of mirage, then our sense of existing in a solid, stable world might be nothing more than a convenient fiction. In this view, what we see and touch is not the true nature of reality, but a kind of projection or appearance. The real universe, if it exists at all, remains hidden from us, beyond the reach of our observations. In the many worlds interpretation, the observer plays a passive role. When we make an observation, we simply become part of the branching process, with one version of us continuing in each new universe. The observer doesn't determine which reality becomes real. Instead, all possible realities coexist, each in its own universe. Reality, in this view, is objective and independent of our observations, even if it is fragmented into countless parallel universes. In contrast, the idea that reality is an illusion suggests that the observer plays a much more active role. Here, reality depends on our act of observation. The universe we experience is not an objective entity, but a kind of construct, created by the interaction between our minds and the quantum world. Without an observer, there is no reality, just a cloud of possibilities that never collapse into anything real. This raises the question of whether the universe exists at all when no one is looking. Is there a real world out there, independent of our perceptions, or is reality nothing more than a projection brought into being by our observations? Quantum decoherence. How does reality solidify? Quantum decoherence is one of the most important processes in quantum mechanics that helps bridge the strange behavior of particles at the quantum level with the stable, predictable world we experience. It provides a framework for understanding how the many possibilities inherent in a quantum system resolve into a single, observable reality. At its core, decoherence is the process by which a quantum system loses its quantum characteristics and behaves more classically, meaning it starts to follow the familiar laws of physics that we experience every day. In quantum mechanics, particles can exist in a superposition of multiple states at the same time. A particle might spin in two directions at once or exist in two places simultaneously, but we never observe this directly. In our daily lives, we only ever see one version of these possibilities, which raises the question: how does reality seem to solidify from the strange behavior of quantum particles into the concrete world we observe? This is where quantum decoherence comes into play. When a quantum system interacts with its environment, the system becomes entangled with the environment. This means that the different possible states of the quantum system become linked to different states of the environment. Over time, the interaction with the environment causes the quantum superpositions to decohere, meaning that the system no longer behaves as if it were in a superposition of states. Instead, it behaves as if it has settled into one specific state, which is what we end up observing. Imagine a simple example: a single electron that can exist in two places at once. Before any interaction with the environment, this electron is in a superposition, meaning it is in both places simultaneously. However, as soon as the electron interacts with anything in its surroundings, like a photon, an atom, or even the air, it becomes entangled with these particles. The superposition states of the electron get linked with different environmental conditions. As more interactions happen, the coherence of the superposition breaks down, and it becomes impossible to observe the electron in both places. Instead, the electron appears to be in one specific location. This is quantum decoherence at work, the collapse of possibilities into the observable world. One way to understand decoherence is by thinking of it as the environment measuring the quantum system, but without us directly observing the process. The environment doesn't necessarily choose one outcome over another. Instead, the system loses its quantum nature, meaning it no longer behaves as if it exists in multiple states at once. This helps explain why, in our everyday experience, objects don't appear in superpositions of multiple places or states. Decoherence effectively hides the weirdness of the quantum world from us, leaving only the stable, classical reality we observe. However, decoherence doesn't necessarily mean that the quantum system has collapsed into one single state. This is an important distinction. In quantum mechanics, decoherence and the collapse of the wave function, the mathematical description of a quantum system, are often discussed together, but they are not the same thing. Decoherence is a physical process that happens due to the interaction between a quantum system and its environment, while the collapse of the wave function is a theoretical concept that describes how quantum possibilities reduce to one observed outcome. In other words, decoherence tells us why we don't observe superpositions, but it doesn't fully explain why a particular outcome is chosen when we make a measurement. That's where interpretations of quantum mechanics like the many worlds interpretation or the Copenhagen interpretation come in. According to the many worlds view, decoherence causes the different possibilities to branch into separate universes, meaning all outcomes occur, but in different realities. In the Copenhagen interpretation, decoherence is part of the process that leads to a single outcome being observed when a measurement is made. Without decoherence, we would expect to observe much more quantum strangeness in our daily lives. Imagine trying to sit on a chair that could exist in multiple locations at once, or trying to drink from a cup that might be simultaneously empty and full. Decoherence prevents these kinds of paradoxes from spilling over into our experience. It helps ensure that, at the macroscopic level, reality behaves in a way that makes sense, following predictable laws of physics. But what happens when decoherence doesn't occur properly, or when quantum effects become significant at larger scales? This is an area that remains largely theoretical, but could have fascinating implications for our understanding of reality. Some researchers speculate that certain systems, particularly those that are well isolated from their environment, could maintain their quantum coherence for extended periods. This would allow these systems to remain in superposition, behaving in ways that defy classical physics. One such example is found in quantum computing. Quantum computers rely on qubits, which are quantum systems that can exist in superpositions of multiple states. In order to perform computations, quantum computers must maintain coherence in their qubits long enough to process information. This is a delicate task because any interaction with the environment could cause the qubits to decohere, collapsing their superposition and ruining the calculation. Quantum decoherence is one of the biggest challenges in building reliable quantum computers, as it threatens to disrupt the quantum processes that give these computers their power. In the realm of biology, there is ongoing research into whether quantum coherence could play a role in certain biological processes. Some scientists have proposed that quantum effects might be at work in processes like photosynthesis, where plants convert sunlight into energy with remarkable efficiency. The idea is that quantum coherence could allow energy to be transported through the system in multiple pathways at once, optimizing the process. While this remains a speculative area of study, it opens the door to the possibility that quantum mechanics might have more influence over the macroscopic world than we currently understand. Does quantum information define reality? Quantum mechanics has long challenged our understanding of the physical world, and as we move further into the strange and fascinating world of quantum theory, an intriguing idea emerges: that the universe, at its most fundamental level, might not be defined by matter, but by quantum information. If true, it would mean that what we perceive as physical objects are simply manifestations of deeper informational structures. Quantum information is not the same as the classical information we are used to dealing with in everyday life. In the classical world, information can be measured in bits, which represent either a 0 or a 1. Computers, for example, process information in this binary format. But in the quantum world, information is stored in qubits, which can exist in a superposition of both 0 and 1 simultaneously, much like how quantum particles can exist in multiple states at once. This gives quantum information unique properties that don't align with our everyday experiences. One of the key features of quantum information is that it cannot be copied in the same way that classical information can. This is known as the no-cloning theorem, which states that it's impossible to make an exact copy of an unknown quantum state. This contrasts with classical information, where we can freely duplicate data without consequence. The inability to copy quantum information introduces a level of uncertainty and fragility to the data, implying that information in the quantum world has a different, more fundamental role in shaping reality. In this view, particles, atoms, and even larger objects are not the true building blocks of reality. Instead, they are the result of underlying informational processes that give rise to the physical world we observe. The idea that quantum information could define reality suggests that the universe operates much like a quantum computer, processing information at a level far deeper than we can directly perceive. This has led some scientists to propose that the physical world is, in a sense, a kind of output of quantum information processing. In this context, entanglement is a great example of a kind of information flow that doesn't respect the boundaries of space and time. The connection between particles exists on an informational level, suggesting that physical objects are secondary to the information they embody. If information is the foundation of reality, then the space-time framework we use to understand the universe is not the most fundamental layer of existence. Instead, space and time may emerge from the deeper quantum informational structure, just as physical objects do. This shift in thinking has also led to new ways of exploring the universe. In recent years, scientists have begun to study the role of quantum information in black holes. For many years, physicists believed that when something falls into a black hole, all the information about that object is lost forever. This created a problem known as the black hole information paradox, because according to the laws of quantum mechanics, information cannot be destroyed. To resolve this paradox, researchers are now looking at the role of quantum information in black holes. One of the leading ideas is that the information about objects that fall into a black hole is not destroyed, but stored on the event horizon, the boundary of the black hole. This is known as the holographic principle, which suggests that all of the information about the three-dimensional space inside the black hole is encoded on its two-dimensional surface. If the universe operates according to similar principles, it could mean that everything we perceive as a three-dimensional reality is in fact a projection of quantum information stored on a lower dimensional surface. The physical objects and spaces we interact with may be akin to holograms, manifestations of the underlying informational structure. This is not just a theoretical idea. It is being tested in various ways, including experiments that aim to detect the pixelation of space itself, much like how a digital image is made up of individual pixels. If space is composed of discrete units of information, it would provide further evidence that the universe is fundamentally informational. The holographic principle: is the universe just a 2D projection? The holographic principle, rooted in both theoretical physics and cosmology, challenges our understanding of reality by suggesting that the three-dimensional world we observe could be an illusion, much like a hologram. Developed in part by Dutch physicist Gerardus Hooft and later expanded by Leonard Susskind, they proposed that the information about objects falling into a black hole isn't lost, but is instead encoded on the event horizon, the two-dimensional boundary of the black hole. This encoding would allow the information to be preserved, even as the black hole itself eventually evaporates. In this sense, the event horizon acts like a hologram, storing all the information about the objects inside in a two-dimensional form. This idea, though initially developed to solve the black hole information paradox, has far-reaching implications for our understanding of the entire universe. If the holographic principle applies to black holes, it might apply to the universe as a whole. This leads to the astonishing suggestion that everything within the universe, including space-time itself, could be described by information stored on a distant two-dimensional surface, possibly at the edge of the universe. In this view, what we perceive as a three-dimensional world with depth and volume could be a projection of information encoded on a flat surface, much like how a hologram creates a three-dimensional image from a two-dimensional film. The objects we interact with, the distances we measure, and even the passage of time could be part of a vast, intricate projection. The holographic principle has gained support from several areas of theoretical physics, particularly in string theory, where it provides a framework for understanding how gravity works in a universe with more than three dimensions. According to string theory, the universe may have extra spatial dimensions beyond the familiar three, and the holographic principle helps to explain how gravity behaves in this higher dimensional space. One of the most famous applications of the holographic principle is in the study of anti-de Sitter space, a type of curved space-time that arises in certain solutions to Einstein's equations of general relativity. In this context, the holographic principle takes the form of the anti-de Sitter conformal field theory correspondence, or ADS-CFT for short, which relates a gravitational theory in a higher dimensional space to a quantum field theory on the lower dimensional boundary of that space. This correspondence has provided valuable insights into the behavior of black holes and quantum gravity, as well as a deeper understanding of how the holographic principle works in practice. Virtual particles. How real are the building blocks of matter? In the strange world of quantum mechanics, one of the more perplexing ideas is the existence of virtual particles. These particles aren't like the stable familiar particles that make up the atoms in our bodies, or the matter we interact with every day. Instead, virtual particles are fleeting entities, constantly appearing and disappearing within the quantum vacuum. This phenomenon raises profound questions about what constitutes the building blocks of reality, and whether even the smallest components of matter are as real as we once thought. The quantum vacuum, often described as empty space, is far from empty. Instead, it is teeming with activity at the quantum level. According to quantum field theory, the vacuum is a seething, restless place where fields permeate all of space, even in regions with no matter. These fields fluctuate continuously, giving rise to virtual particles that pop into existence and vanish just as quickly. These particles never linger long enough to be observed directly, and yet their existence can have measurable effects on the physical world. In the 1940s, Dutch physicist Hendrik Casimir proposed that two uncharged metal plates placed very close together in a vacuum would experience an attractive force due to the presence of virtual particles. This Casimir effect has since been observed experimentally, confirming that the fluctuations in the vacuum, driven by virtual particles, can exert a physical force on objects. Virtual particles are not considered real in the same sense as electrons or protons, which can be directly detected and observed. They exist for only the briefest of moments, arising from the vacuum's fluctuations and then annihilating each other almost immediately. Virtual particles can be thought of as disturbances in the underlying quantum fields, temporary ripples that never fully solidify into real matter. What's even more intriguing is that these virtual particles play an essential role in some of the most fundamental forces of nature. For example, in quantum electrodynamics, or QED, virtual particles are responsible for mediating the electromagnetic force. When two charged particles interact, they exchange virtual photons, which carry the electromagnetic force between them. Though these virtual photons are not directly observed, they are essential to the interaction, suggesting that the forces we rely on to understand the universe are, in part, governed by entities that are not fully real in the classical sense. The concept of virtual particles also appears in quantum chromodynamics, or QCD, the theory describing the strong force that holds atomic nuclei together. In this framework, virtual particles called gluons constantly exchange between quarks, binding them together to form protons and neutrons. Without this exchange of virtual particles, the fundamental structure of matter as we know it would cease to exist. Once again, we find that the forces shaping the universe rely on the existence of virtual particles, which themselves challenge our understanding of what is real. The idea that something can exist briefly, yet still have tangible effects, poses an intriguing philosophical question. If virtual particles are not real in the traditional sense, but they influence measurable outcomes, what does this say about the nature of reality? Are they simply mathematical tools we use to describe forces and interactions? Or do they suggest that even the fundamental fabric of the universe is composed of transient, ill-defined entities? The existence of virtual particles also hints at deeper questions about the structure of reality itself. If the very vacuum of space is teeming with these transient particles, is it accurate to think of the vacuum as empty at all? In a sense, the idea of nothingness becomes problematic in the quantum world, where even what we consider empty space is filled with fluctuating energy fields and the potential for virtual particles to emerge. Perhaps what we perceive as solid, stable matter is just one level of a more complex dynamic system, where fluctuations and probabilities define the basic structure of reality. If the building blocks of matter can emerge and vanish within the quantum vacuum, it suggests that reality is not as concrete as we experience it on a day-to-day basis. Instead, what we consider real may be just a temporary arrangement of underlying quantum information and fluctuations. Black holes and information paradox, a crisis for reality itself. Black holes have always been a subject of fascination and mystery. These cosmic objects, with their immense gravitational pull, are powerful enough to trap anything that crosses their event horizon, including light itself. But what happens to information that falls into a black hole? The black hole information paradox arises from this very question and has created a crisis for our understanding of reality. In classical physics, when an object is thrown into a black hole, it is lost from our view forever. But in the 1970s, physicist Stephen Hawking introduced the idea that black holes are not entirely black. They can emit radiation, now known as Hawking radiation, and over time, this radiation causes the black hole to slowly evaporate and disappear. If this is true, then what happens to all the information that was inside the black hole? In physics, information plays a central role. Every particle, every wave, carries some amount of information. This information describes the state of a system, where particles are, how they are moving, and what their properties are. According to the principles of quantum mechanics, this information can never be destroyed, even if the particles themselves change form. This is a fundamental rule known as the conservation of information. But if a black hole evaporates completely, as Hawking radiation suggests, the information about everything that fell into it would be lost. This seems to break one of the most basic laws of quantum mechanics. The dilemma then is stark. Either black holes do destroy information, which contradicts quantum mechanics, or our understanding of black holes and the nature of space-time itself is deeply flawed. The black hole information paradox has thus become a focal point for debates on the nature of reality. One way to think about the paradox is to consider what happens to objects that fall into a black hole. Imagine throwing a book into a black hole. The book contains a vast amount of information: the arrangement of its atoms, the words on its pages, the ink's chemical composition. Once it crosses the event horizon, the point of no return, this book is lost to the outside world. But does this mean that all the information the book contained is erased from existence? According to classical physics, yes, the book is gone and the information with it. However, quantum mechanics tells a different story. The theory insists that information about physical states cannot be destroyed, which brings us back to the central paradox. Stephen Hawking's solution, that black holes emit radiation and slowly evaporate, added another layer of complexity. As the black hole shrinks due to Hawking radiation, it releases energy, but not information. Once the black hole has fully evaporated, the information that fell into it seems to vanish, violating the conservation of information. This presents a major conflict between general relativity, which describes black holes and space-time, and quantum mechanics, which governs the behavior of particles and information. If information can be lost, then it calls into question the very laws that describe the universe at a fundamental level. Physicists have proposed various solutions to resolve this paradox, each more mind-bending than the last. One idea is that the information is somehow encoded in the Hawking radiation itself, though in a highly scrambled form. This would mean that even though the black hole disappears, the information about everything that fell into it is still present, just incredibly difficult to decipher. Another possibility is that black holes might not truly destroy information, but instead store it in some hidden, unknown way. This concept connects to the holographic principle. The idea is that, much like a hologram, the three-dimensional information inside the black hole is encoded on its two-dimensional boundary. And in theory, this information remains intact, even as the black hole evaporates. Yet another radical idea is that black holes could act as gateways to other universes, with information being transported through a kind of cosmic wormhole to another region of space-time. In this scenario, the information is not lost, but rather displaced to a different universe or dimension, far beyond our ability to detect, perhaps out of a corresponding white hole that is an equal but opposite version of a black hole. A white hole would constantly be spewing out mass, light, energy, and information, but nothing would be able to enter into it. Nothing could make its way past the white hole's event horizon. The black hole information paradox has taken on such significance in theoretical physics because it threatens to unravel the foundational principles of both quantum mechanics and general relativity. The fact that two of our most successful and well-tested theories cannot coexist peacefully in the face of black holes suggests that something is missing from our understanding of the universe. It also raises philosophical questions about the nature of existence. If information can be lost, does that mean objects or events that fall into a black hole cease to exist in any meaningful way? Does the black hole represent a boundary not just for physical objects, but for reality itself? And if so, is reality contingent upon the ability to preserve information? The role of consciousness in defining the universe. The question of whether consciousness itself plays a role in defining the universe has sparked intense debates across both science and philosophy. At its core is the implication of quantum mechanics that particles seem to exist in multiple states until they are observed. This phenomenon suggests that before observation, particles do not have definite positions or states. Only when they are observed, when someone or something interacts with them, do they collapse into one specific state. If observation is what forces reality to take shape, can the universe even exist without an observer? This observer effect suggests that the act of observing a quantum system alters the system in a fundamental way. Take, for instance, the famous double-slit experiment. In this experiment, particles like electrons are fired at a screen through two slits, creating a pattern on the screen behind the slits. When not observed detected, the particles behave like waves, creating an interference pattern, as though they passed through both slits at once. However, when the particles are observed, they behave like particles, passing through one slit or the other, and the interference pattern disappears. It is as if the mere act of watching the particles forces them to make a choice, collapsing the wave-like behavior into a particle-like one. Without an observer, quantum particles remain in a state of uncertainty, existing in multiple possibilities at once. When an observer becomes involved, these possibilities collapse into a single outcome. In the context of the entire universe, this raises a striking question. Does the universe exist independently of us, or does it require observers, conscious beings, for it to take shape? If observation is necessary to collapse quantum possibilities into a specific reality, could it be that consciousness itself is a fundamental part of the fabric of reality? The Copenhagen interpretation of quantum mechanics, developed by physicists Niels Bohr and Werner Heisenberg, suggests that quantum particles do not have a definite state until they are measured or observed. According to this view, it is the act of measurement or observation that brings particles into a concrete state, implying that the physical universe may not have a defined reality without the intervention of an observer. Some physicists and philosophers have taken this a step further, arguing that consciousness itself might be the key to the universe's very existence. They propose that reality is not objective, existing independently of us, but rather subjective, shaped by our perceptions. In this view, the universe exists in a kind of potential state, full of quantum possibilities, until consciousness interacts with it and collapses those possibilities into the reality we experience. This notion, however, is not without its critics. Many argue that to say consciousness creates reality is to misunderstand the role of observation in quantum mechanics. Observation, they suggest, does not necessarily require a conscious observer. It could be any kind of interaction that forces particles to take on definite states. For instance, when a photon interacts with an electron, it effectively observes the electron, causing it to collapse from a superposition of states into a specific one. In this sense, observation might simply be any physical interaction, rather than a process involving consciousness. Wigner's friend. Can different observers have different realities? Wigner's friend experiment presents an intriguing and thought-provoking scenario. Can different observers experience different realities? It builds upon the foundations of quantum mechanics, particularly the idea that observation plays a crucial role in determining the state of a system. In quantum physics, observation is not a passive act. It's an interaction that can cause quantum particles to collapse from a superposition of states into one specific outcome. This experiment, proposed by physicist Eugene Wigner, pushes this concept further by considering whether two observers can disagree on what reality actually is. The thought experiment is a variation of the famous Schrödinger's cat scenario. Imagine a quantum system like a particle that is in a superposition, existing in multiple states simultaneously. In Wigner's version, his friend is placed inside a laboratory to observe the quantum system. At the same time, Wigner remains outside the lab, unaware of what the friend observes. Inside the lab, the friend performs a measurement on the quantum system, collapsing the particle's state to a definite outcome. From the friend's point of view, the act of observation leads to a clear result. The quantum system is no longer in superposition, but instead has taken on one specific state. This outcome seems real and objective to the friend because they observed it firsthand. But from Wigner's perspective outside the lab, the situation is entirely different. Until Wigner opens the door and interacts with the system inside, the quantum state of both the particle and his friend are still in superposition. From Wigner's vantage point, both the particle and the friend exist in a state of multiple possibilities. This leads to a strange paradox. Inside the lab, the friend experiences one reality, a definitive outcome. Outside, Wigner still sees the entire situation as undefined, with multiple outcomes existing simultaneously. So who is right? Does the friend's observation dictate what is real, or is Wigner's broader view just as valid? In some interpretations of quantum mechanics, this leads to the idea that there is no such thing as a universal or shared reality. Instead, each observer constructs their own version of reality based on the information they gather from their interactions with quantum systems. This has philosophical implications that extend beyond physics into questions of perception, truth, and the nature of consciousness itself. To test ideas like those proposed in Wigner's friend experiment, physicists have designed experiments using quantum systems to measure how different observers might experience different outcomes. These experiments continue to push the boundaries of our understanding of quantum mechanics and the role of observation in shaping reality. While no definitive answer has emerged, what's clear is that the relationship between observers and the universe they observe is more complex than previously thought. Simulation theory. Could we be living inside a quantum computer? An intriguing attempt on reconciling the nature of our strange reality comes in the form of simulation theory, which presents to us the idea that our reality might be nothing more than an elaborate simulation, possibly run on a highly advanced quantum computer. In this view, the universe itself is a computational process, unfolding through the interaction of information. Quantum mechanics, with its strange behaviors and outcomes, seems to support the idea of a simulated universe. The unpredictable nature of quantum particles, the way they only appear in definite states when observed, and the concept of entanglement all appear consistent with a virtual reality, where information is processed and updated based on the interactions within the simulation. If our reality were simulated, it could explain why certain aspects of quantum mechanics, like superposition and entanglement, seem so difficult to fit within our classical understanding of the universe. After all, the behavior of particles at the quantum level doesn't necessarily align with how we expect the physical world to behave. A simulation, however, wouldn't need to follow the same rules. In fact, it might operate under a completely different set of principles that are only partially revealed to us through the strange phenomena we observe in quantum physics. One of the key ideas behind simulation theory is the concept of computational limits. Just like in a video game, where the virtual world is rendered only when the player looks in a specific direction, quantum particles might only choose a state when they are observed. This would be a more efficient way for a simulation to run, conserving resources by not rendering unnecessary details until they become relevant. The process of observation in quantum mechanics, where particles collapse from superpositions into definite states, mirrors this idea. It's as if the universe doesn't bother to calculate the state of a particle until someone is looking at it. In a simulated universe, entanglement could simply be a form of programming, where two particles are linked by an underlying code that ensures their states are synchronized, no matter how far apart they are. To us, this would look like a mysterious, faster-than-light connection. But in a simulation, it's just the program updating both particles based on the same set of instructions. This could account for the non-local behavior we see in entanglement, where changes in one particle instantly affect another, regardless of distance. One of the central challenges in proving simulation theory is that, if it were true, it would be difficult to detect. Much like characters in a video game have no way of knowing they're inside a game, we might lack the tools or perspective to see beyond the boundaries of our simulated reality. However, some physicists have suggested that there could be clues hidden within the fabric of the universe. For example, if the universe were a simulation, we might expect to find evidence of limits or boundaries, much like the pixelation that occurs when you zoom in too far on a digital image. Some researchers have even proposed that the apparent granularity of space and time at the smallest scales, as described by quantum mechanics, could be a sign that we are living in a simulation. Just as a computer-generated image is composed of individual pixels, the universe might be made up of tiny, discrete units of space and time, Planck lengths and Planck times, suggesting that the universe operates on a computational grid. Another potential clue comes from the fine-tuning problem in cosmology. The fundamental constants of the universe, such as the strength of gravity, the charge of the electron, and the cosmological constant, appear to be finely tuned in such a way that they allow for the existence of life. In a simulated universe, this fine-tuning might be intentional, designed to create a stable environment where complex structures, like galaxies, stars, and planets, can form, and where life can evolve. Are the programmers simply running an experiment to see what happens? Or is there a purpose behind the simulation's design? One of the more provocative ideas associated with simulation theory is that if we are living in a simulation, it's possible that the simulation could be altered or even shut down at any time. Just like a video game can be paused, restarted, or deleted, our reality could be subject to instantaneous changes beyond our control. If the simulation were to end, would we even be aware of it, or would we simply cease to exist? Nick Bostrom's simulation argument, a question of probabilities. Many people have tried to argue that the simulation theory is not just possible, but in fact probable. Famously, Nick Bostrom's simulation argument presents a probabilistic case that suggests it's more likely than not that we are living in a simulated reality. The reasoning behind this is based on a few key assumptions about the future development of civilizations and their technological capabilities. If advanced civilizations reach a point where they can create incredibly detailed simulations of reality, simulations so intricate that the beings within them are conscious, then the chances that we are in the base reality, as opposed to a simulation, become quite slim. Bostrom's argument starts with three possibilities, one of which he believes must be true. The first is that civilizations never reach the technological level needed to create such advanced simulations. The second is that even if they can create these simulations, they choose not to. The third possibility is that civilizations do create many such simulations, and if that's the case, then the odds that we are living in the original reality rather than one of these many simulations are very low. Bostrom suggests that unless there's something inherent in the development of civilizations that prevents them from reaching the technological ability to create simulations, or they collectively decide not to engage in simulation technology, the third scenario is the most likely. This reasoning stems from a simple idea of probability. If countless simulations exist, each populated with beings that are unaware they're in a simulation, then we would have no special reason to believe that we are living in the real reality. Instead, it would be statistically more likely that we are one of the many simulations running within some kind of advanced computer system, perhaps controlled by a civilization far beyond our own level of understanding. Multiverse or matrix. Are these concepts one and the same? The multiverse theory and the simulation hypothesis are two ideas that push the boundaries of our understanding of reality, but they often seem to come from different areas of thought. Yet, as different as these two concepts may appear, they could share surprising common ground. Could it be that the multiverse theory and the simulation hypothesis describe the same thing from different perspectives? Could the many universes of the multiverse all be part of a larger, overarching simulation? Consider the possibility of nested simulations. If we are living in a simulation, it's possible that the beings or entities running our simulation are themselves living in a simulated universe. In this scenario, simulations could stack upon one another, with each layer of reality being the product of a higher-level simulation. If this is the case, then the multiverse could be a vast network of interconnected simulations, each nested within another. This would mean that there isn't just one overarching simulation, but a multiverse of simulations, with no clear boundary between real and simulated universes. If every possible quantum event creates a branching universe, these branches could be seen as different instances or versions of a simulated reality. In this sense, The multiverse could be the result of the simulation dynamically generating new universes based on quantum events, much like how a video game might generate new levels or environments as the player progresses. The many worlds interpretation and the simulation hypothesis could be two sides of the same coin, both describing a system where multiple realities coexist, constantly being created and shaped by underlying computational processes. In a sufficiently advanced simulation, it wouldn't be difficult to imagine the system generating multiple versions of reality simultaneously, each with its own set of parameters and outcomes. These simulated realities could operate independently of one another, or they could interact in subtle ways, much like the parallel universes described by the multiverse theory. From this perspective, the multiverse and the simulation hypothesis don't just overlap. They might be describing the same thing. There's also the question of whether a simulated multiverse would be distinguishable from a real multiverse. If we are living in a simulation, and if that simulation contains many different universes, how could we ever know whether those universes are real or simulated? In practical terms, there might be no difference. From the inside of the simulation, each universe would appear as real and tangible as any other. The inhabitants of each universe, whether they are aware of the simulation or not, would experience their own reality just as we experience ours. In this sense, the distinction between a real multiverse and a simulated one might be irrelevant. Quantum simulations. Do we already simulate reality? Quantum simulations are already a significant part of modern science, especially in the field of quantum mechanics and computing. By simulating reality on a quantum level, scientists are pushing the boundaries of what we understand about the universe and how we might one day create our own simulated realities. Quantum simulations use the principles of quantum mechanics to model highly complex systems that classical computers struggle to handle. These simulations represent a bridge between theory and practical application, demonstrating that the concept of creating simulated realities is not theoretical, but actually unfolding in our labs today. Quantum simulations have the ability to replicate natural processes with a degree of accuracy that traditional simulations cannot achieve. Classical computers, for all their processing power, operate based on binary logic. This is highly efficient for many tasks, but falls short when trying to model quantum systems, which are not confined to this either-or framework. In the quantum world, particles exist in superpositions of states, can be entangled, and exhibit behaviors that don't conform to classical expectations. Quantum simulations use the capabilities of quantum computers to mimic the behavior of quantum systems, from the smallest particles to larger, more complex systems like molecules, or even entire environments. By processing information in a way that mirrors the probabilistic nature of quantum mechanics, they simulate reality on a much more fundamental level. One of the key strengths of quantum computing is its ability to handle complex systems with many interacting components. In a classical system, simulating these interactions quickly becomes intractable. The number of calculations required grows exponentially as more variables are added. Quantum computers, on the other hand, process information in parallel due to the principle of superposition, where qubits can exist in multiple states simultaneously. This allows quantum computers to explore multiple possibilities at once, effectively enabling them to simulate far more complex systems than classical computers ever could. An example of quantum simulation in action is in the field of chemistry. Chemical reactions are inherently quantum processes, involving the interactions of electrons and atoms that follow quantum mechanical rules. Understanding these reactions at a fundamental level can be incredibly difficult for classical computers, as the sheer number of variables and possible states becomes overwhelming. With quantum simulations, however, scientists can model these reactions with much greater precision. By simulating molecules and their interactions on a quantum level, researchers can predict the outcomes of chemical reactions more accurately, potentially leading to breakthroughs in fields like drug discovery, materials science, and renewable energy. The development of new materials often depends on understanding how atoms and molecules interact on a quantum level. For example, the quest to create superconductors, materials that can conduct electricity without resistance, relies heavily on quantum simulations. By modeling the quantum interactions in these materials, scientists hope to discover new superconductors that work at higher temperatures, which could revolutionize energy transmission and storage. Similarly, quantum simulations are being used to study exotic states of matter, such as quantum spin liquids and topological insulators, which have potential applications in quantum computing and other advanced technologies. Quantum simulations are also being used to explore phenomena that are otherwise too difficult to study in real life, such as the behavior of particles in extreme environments like the interiors of black holes or the early universe. These are places where the laws of physics as we know them start to break down, and where experimental data is difficult, if not impossible, to obtain. By using quantum simulations, scientists can explore these extreme environments in a virtual space, gaining insights that would otherwise be out of reach. By tweaking the parameters of a quantum simulation, scientists can even explore scenarios where the laws of nature are entirely different. These experiments allow us to explore what other universes might look like, whether they are governed by different forces, different dimensions, or even entirely different types of matter. For example, in our universe, we rely on 4 fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. These forces are responsible for shaping the structure of everything from atoms to galaxies. But what if we lived in a universe with only 2 fundamental forces, or 10? Quantum simulations allow us to play with these variables, exploring what reality might look like if the very building blocks of nature were altered. We could examine worlds where gravity doesn't exist, or where it dominates all other forces, where light behaves in unexpected ways, or where time itself flows differently. By creating simulations that deviate from the physical laws we know, we might stumble upon new insights into how our reality works. For instance, simulating universes without gravity might help us understand why gravity is so weak compared to the other fundamental forces. Or simulating universes with different space-time geometries might give us clues about the true nature of dark energy, which is currently one of the biggest mysteries in cosmology. In this way, quantum simulations of alternate realities could become a powerful tool for scientific discovery, offering new perspectives on age-old questions about the universe. In many ways, the use of quantum simulations is already bringing us closer to the ability to create simulated realities. While we are not yet at the point where we can simulate entire universes or conscious beings, the foundational technologies are being developed right now. As quantum computing continues to advance, the complexity and scope of these simulations will only grow. It's conceivable that we could someday create simulations of reality that are so detailed and accurate that they become indistinguishable from the real thing. In the future, it's possible that quantum simulations could go beyond the physical and venture into the realm of consciousness and artificial intelligence. If quantum computers can simulate complex quantum systems, might they also be capable of simulating the human mind? Could they create artificial intelligences that experience their own version of reality, perhaps even believing themselves to be conscious beings? This idea takes us into the realm of ethical questions about the nature of simulated beings and whether their experiences should be considered real. If a quantum simulation can replicate the processes of a human brain, is the simulated mind any less real than our own? Digital physics. Is the universe a code we can crack? If the universe at its most fundamental level operates like a giant computational system, then instead of being composed of continuous waves or solid matter, everything we see around us could be built from discrete units of information, much like how a computer processes data through binary code. This theory, called digital physics, has gained traction among some scientists and philosophers, as it offers a way to explain the strange behavior of particles in quantum mechanics and the seeming unpredictability of the universe. By thinking of the universe as a digital system, one might imagine that reality is structured like a code, a set of instructions or algorithms governing how everything behaves. If the universe is fundamentally digital, then what we think of as solid matter might not really be solid at all. Instead, matter could be seen as information that takes on a physical form, but only because the underlying code dictates it to do so. Just as a digital image on a computer screen appears solid to the eye, but is really just a collection of pixels, controlled by underlying software, physical objects might be no more than manifestations of deeper computational rules. One of the key ideas behind digital physics is that the universe could be broken down into the smallest possible units. Think of these as the bits of the universe, just like the bits that make up data in a computer. These units might represent tiny quantities of energy, space, or time, and together they form the building blocks of everything. In this way, digital physics suggests that the universe is not infinitely divisible. There is a limit to how small things can get, and at that level, the universe functions as a vast computational grid, processing these basic bits of information. If this is true, then the universe could be seen as operating like a giant simulation, where the fundamental laws of physics are the rules of the program, and everything we observe follows those rules. Just as a video game has its own internal logic, where certain things can and cannot happen based on how the game was coded, our universe could be similarly restricted by its own set of computational rules. These rules might explain why particles behave the way they do, jumping between states or existing in multiple places at once, because in a digital system, things are not always continuous or smooth. Instead, everything is processed in steps, much like how a computer operates through discrete calculations. Some proponents of digital physics point to the fact that the universe appears to have a finite structure. For example, the speed of light is a universal constant. Nothing can travel faster than light, and this acts as a fundamental limit on how information can move across the universe. Similarly, space itself seems to be made up of discrete units. This is suggested by the fact that, at very small scales, space behaves strangely, as if it's not a smooth continuum, but a patchwork of tiny pixels of space. This idea ties into the broader notion that the universe might be governed by something similar to a computational grid, where the space-time continuum is actually a finely divided lattice of tiny units. Another fascinating aspect of digital physics is how it relates to the idea of time. In classical physics, time is viewed as a continuous flow, moving smoothly from one moment to the next. But in a digital universe, time might not be continuous at all. Instead, it could be broken down into tiny increments, like the frames of a movie or the ticks of a computer clock. Each tick represents a single moment in time, and the universe moves from one moment to the next in a step-by-step process. This would mean that time, like space, is not infinitely divisible. It has a smallest possible unit beyond which there is no finer division. Some scientists have suggested that we might one day be able to crack the code of the universe, discover the underlying algorithms that govern how everything works. Just as we can reverse engineer a piece of software to understand how it was programmed, we might one day reverse engineer the universe to uncover the fundamental rules that govern reality. This would be the ultimate goal of physics, not just to describe how the universe behaves, but to understand the deep underlying logic that creates everything we observe. Quantum Zeno effect. Does reality freeze when observed? The quantum Zeno effect is a phenomenon that seems to defy our intuitive understanding of time and change. In classical terms, we expect that things evolve smoothly over time. For example, if you watch a pot of water on the stove, it eventually boils. But in the quantum world, frequent observation can have a very strange impact on how systems evolve. The quantum Zeno effect suggests that by observing a quantum system continuously or at very short intervals, you can effectively freeze its state, preventing it from evolving as it normally would. This effect gets its name from the ancient Greek philosopher Zeno of Elea, who is best known for his paradoxes. especially the idea that motion is an illusion. One of Zeno's famous paradoxes is the arrow paradox, where he argues that an arrow in flight at any given instant of time is at rest in a specific position. If you continuously observe the arrow at every single moment, it doesn't appear to move. In other words, if there is no motion at any given moment, and time is made up entirely of these moments, then motion should not occur at all. Of course, in our everyday world, we know that arrows do move and reach their targets. But in the quantum realm, this kind of logic seems to hold. Continuous observation can halt change. The quantum Zeno effect is closely tied to the concept of wave function collapse. In quantum mechanics, particles exist in a superposition of states until they are observed or measured. Once observed, the wave function collapses, and the particle takes on a definite state. The Zeno effect occurs when a quantum system is measured so frequently that the wave function keeps collapsing back to the same state, effectively preventing the system from evolving into another state. An example of this is a quantum system, such as an atom that is in an excited state and is about to decay to a lower energy level. Under normal conditions, the atom will eventually transition to the lower energy state, emitting a photon in the process. However, if you keep observing the atom's state continuously, the atom will be frozen in its excited state, never decaying as it normally would. The frequent measurements essentially trap the atom in its current condition, preventing the natural evolution of the system. This freezing effect might sound counterintuitive. After all, why should watching something prevent it from changing? The answer lies in the peculiarities of quantum measurement. In the quantum world, the act of measuring a system isn't just a passive process of observation. It actively influences the system, forcing it into one of its possible states. The more frequently you measure it, the more often you collapse its wave function back into its original state. So, rather than allowing the system to naturally evolve, you're constantly resetting it, like hitting a pause button over and over again. One experiment that demonstrated the quantum Zeno effect was conducted in the 1990s, using cold ions. In this experiment, scientists observed ions in a certain quantum state, which was expected to evolve over time. They found that by applying frequent measurements to the system, they could suppress its evolution, confirming the theoretical predictions of the Zeno effect. The ions were essentially stuck in their initial state, unable to progress as they would without observation. The problem of time. Does time exist in a universe that doesn't? Time is one of the most mysterious aspects of the universe. Our everyday experience tells us that time is something continuous, something that flows from one moment to the next, always in one direction. But when we look deeper into the laws that govern the universe, especially through the lens of quantum mechanics, time starts to appear less clear-cut. The concept of time itself becomes difficult to define, and in some interpretations, it might not even exist in the way we traditionally think. In Einstein's view, time is not absolute at all. Instead, it is relative, changing depending on how fast you're moving, or how close you are to a massive object. Time can stretch and compress, a phenomenon called time dilation. Someone moving at a very high speed or near a massive black hole will experience time more slowly compared to someone standing still or far from any such object. This idea revolutionized our understanding of time, showing that it is not a fixed, universal constant, but something flexible and deeply intertwined with space itself. Yet, as strange as Einstein's theory is, it still treats time as something real, a dimension that can be warped and stretched but still exists. Quantum mechanics, however, introduces even more radical challenges to our understanding of time, especially when combined with the indeterminate nature of the universe. The uncertainty that comes with quantum mechanics, where particles exist in superposition and events happen based on probabilities, raises the question of whether time, as we understand it, even exists in a meaningful way. In many of the equations that describe how quantum systems evolve, time appears as just another variable, much like position or momentum. But there's a curious difference. While position and momentum are linked to real-world measurements, time often seems to be something external to the system itself. In some interpretations, time might not even be a fundamental property of the universe. Instead, it could be something emergent, a product of other processes, rather than a basic feature of reality. One theory that tackles this idea is the Wheeler-DeWitt equation, which attempts to describe the universe as a whole in the framework of quantum mechanics. What's particularly striking about this equation is that it seems to suggest that time doesn't exist at all. It's what physicists call time independent, meaning that time doesn't play a role in how the universe behaves on a fundamental level. This has led some to speculate that time, as we experience it, might just be an illusion, something that emerges from the way we interact with the universe, rather than a fundamental property of the universe itself. If the universe is non-deterministic, existing in a state of superposition until observed or measured, what does that mean for time? Can time still exist in a universe where reality itself is not well defined? One possibility is that time is simply a byproduct of the way we perceive the universe. In this view, time might emerge from the process of observation itself. Just as particles collapse from a state of superposition into a definite state when observed, perhaps time only becomes meaningful when we observe the universe. Without observers, without measurements, there might be no such thing as time, just a universe of possibilities waiting to be collapsed into reality. Another possibility is that time exists in a very different form at the quantum level, one that we can't fully grasp with our classical understanding. Some physicists have proposed that time could be quantized, meaning that it doesn't flow continuously like a river, but instead comes in discrete chunks, like frames in a movie. In this view, time might tick at a fundamental level, with events happening in tiny, indivisible increments of time. This would mean that at the smallest scales, time doesn't flow smoothly, but jumps from one moment to the next, with nothing in between. Our brains are wired to perceive time as something that flows smoothly and continuously, but that doesn't necessarily mean that's how time actually works. It's possible that our perception of time is a kind of illusion created by the way we interact with the world. If the universe is fundamentally indeterminate, existing in a state of probabilities rather than certainties, then time might be a byproduct of our attempts to make sense of that indeterminacy. In this sense, time could be similar to the concept of temperature. Temperature doesn't exist as a fundamental property of individual particles. It's something that emerges from the collective behavior of many particles interacting with each other. In the same way, time might emerge from the collective behavior of quantum systems interacting with observers. Without observers, without measurements, there might be no time, just a universe in superposition, existing in a timeless state of potentialities. Max Tegmark's mathematical universe: Is reality just numbers? Max Tegmark, a Swedish-American physicist, introduced a bold and intriguing hypothesis that challenges how we perceive reality. His theory, known as the mathematical universe hypothesis, suggests that the universe itself is not just described by mathematics, but that it is mathematics. This idea takes the notion of mathematical descriptions to a radical new level, implying that everything we perceive as real, from the stars in the sky to the atoms in our bodies, is ultimately a mathematical structure. For Tegmark, the physical universe is nothing more than an abstract mathematical object. Tegmark's theory challenges the common assumption that mathematics is merely a tool for describing the world. In physics, equations and formulas are used to predict the behavior of particles, forces, and energy. The belief is that these mathematical structures describe physical objects like atoms or planets, which exist independently of the math itself. But Tegmark argues that the reverse is true. The mathematical structures themselves are the fundamental reality. Physical objects, as we perceive them, are simply manifestations of these deeper mathematical truths. At the heart of Tegmark's idea is the concept that all of reality can be reduced to numbers and relationships between those numbers. For example, the laws of physics, which govern the behavior of everything from galaxies to subatomic particles, can be expressed mathematically. Equations like Einstein's famous E equals mc squared are not just descriptions of energy and mass, they are statements about how the universe fundamentally works. According to Tegmark, these equations are more than mere descriptions of the physical world. They are the world. The universe doesn't just follow mathematical rules, it is a mathematical structure. In our everyday experience, we tend to think of physical objects as the most real things in the universe. A tree, for example, feels solid and real because we can see it, touch it, and interact with it. But in Tegmark's view, the tree is nothing more than a collection of mathematical properties. Its shape, size, and even its color can be described in terms of geometry, numbers, and equations. The tree, as a physical object, is secondary to the mathematical structure that underlies it. In this sense, physical objects don't have an independent existence, apart from the math that describes them. They are simply one way that mathematical structures can manifest. Tegmark also proposes that if the universe is fundamentally mathematical, then other mathematical structures might also exist as universes in their own right. In Tegmark's framework, every possible mathematical structure corresponds to a different universe. Some of these universes might have physical laws that are radically different from our own. Others might be completely unrecognizable. But they all exist, simply because they are valid mathematical structures. In everyday life, we make a sharp distinction between things that are real, like physical objects, and things that are abstract, like numbers or ideas. But Tegmark's hypothesis suggests that this distinction is an illusion. If the universe is fundamentally mathematical, then numbers and abstract objects are just as real as physical objects. The number 2, for example, might be just as real as the chair you're sitting on. Both are simply different kinds of mathematical structures. If everything is fundamentally mathematical, then our perception of reality is just a way of interpreting these mathematical structures. When we look at a tree, for instance, we perceive it as a solid object with color and texture. But according to Tegmark, what we are seeing is a mathematical structure that we interpret as a tree. Our brains, which are themselves mathematical structures, process the information in a way that makes sense to us. But this doesn't mean that the tree exists as a physical object in the way we perceive it. What we see as a tree is simply a manifestation of the underlying math. One of the strengths of Tegmark's hypothesis is that it provides a unified framework for understanding the universe. In modern physics, there are many different theories and mathematical models that describe various aspects of the universe, from quantum mechanics to general relativity. But these models don't always fit together neatly. Tegmark's hypothesis suggests that all of these models are simply different expressions of the same underlying mathematical structure. In this sense, the universe is not a collection of separate, disjointed phenomena, but a single, coherent mathematical object. But Tegmark's theory is also controversial. One of the main criticisms is that it's difficult to test or prove. Science traditionally relies on experiments and observations to validate theories. But if the universe is fundamentally mathematical, then how can we observe or test something that exists only as an abstract structure? Critics argue that Tegmark's hypothesis is more of a philosophical idea than a scientific one, since it doesn't make specific predictions that can be tested through experiments. Another challenge is that Tegmark's theory raises questions about the nature of mathematics itself. If the universe is a mathematical structure, then where do these mathematical structures come from? Are they created by the universe, or do they exist independently of it? And if they exist independently, where do they exist? The role of free will in a universe that may not exist. In discussions about the nature of the universe, free will often emerges as a central question. If everything we experience is part of a predetermined system, or, more radically, if the universe itself doesn't exist in the way we traditionally think it does, what does this imply for our ability to make choices? The notion of free will, that we have the capacity to make independent decisions that shape our actions, seems intuitive. Most people operate under the assumption that they can decide what to eat for lunch or choose which career to pursue. But when we dig deeper into the fabric of the universe through the lens of quantum mechanics, the question becomes far more complicated. One of the challenges free will faces comes from determinism. In classical physics, the universe is seen as a clockwork machine, with everything operating according to fixed laws. Under this view, every event is the result of previous causes. If you could know the exact state of every particle in the universe at one point in time, theoretically, you could predict everything that would ever happen in the future. This leaves little room for the idea of free will. If our actions are the inevitable result of prior states of the universe, how can they be truly free? However, quantum mechanics introduced an element of unpredictability into this picture. Unlike the deterministic nature of classical physics, quantum mechanics suggests that on the smallest scales, particles don't behave in strictly predictable ways. Instead, their behaviors can only be described in terms of probabilities. This fundamental uncertainty seems to open the door to free will, because if the behavior of particles is not strictly determined, perhaps human actions aren't either. But the randomness of quantum mechanics doesn't necessarily translate to true free will. Randomness, by definition, is not something we control. If our actions were governed purely by random quantum events, they wouldn't be determined by prior causes, but they wouldn't be free in the way we think of it either. Rather than being determined, our actions would be unpredictable, but still not necessarily within our control. This leaves us in a paradox. Neither complete determinism nor pure randomness offers a satisfying account of free will. In the simulation hypothesis, where the universe might be nothing more than a sophisticated computer program, free will becomes even more uncertain. If we are living in a simulation, our actions might be pre-programmed responses, much like the actions of characters in a video game. While those characters appear to make decisions within the context of the game, they are ultimately controlled by the code running the game. If our universe operates similarly, it raises the possibility that what we perceive as free will is just an illusion created by the underlying program. We might feel like we're making choices, but in reality, those choices could be governed by the rules of the simulation. Philosopher Nick Bostrom's simulation argument suggests that if advanced civilizations develop the capability to run simulations of entire universes, it's more likely than not that we are living in one of those simulations. In such a scenario, free will becomes difficult to maintain as a real concept. But what if the universe, or our perception of it, truly does not exist in the way we think? If, as some interpretations of quantum theory propose, the universe is more like a set of probabilities or potentialities rather than a concrete objective reality, does free will even have meaning in such a context? If the universe is simply a mathematical construct or a series of potential outcomes, it's hard to see where human agency fits in. Without a concrete external reality to act upon, can we still claim to have the ability to make choices? If consciousness plays a role in collapsing quantum probabilities into actual outcomes, then perhaps our ability to make choices influences the very nature of reality. In this view, free will could be tied to the observer effect in quantum mechanics. By observing the world, we might be helping to bring certain realities into existence. But even this doesn't necessarily imply traditional free will. The process of observation in quantum mechanics is not one of deliberate control, but more of passive participation. The observer doesn't choose which quantum state will collapse into reality, they simply observe it. Can physics explain consciousness in a non-physical universe? Consciousness, which is often thought of as an intensely personal and tangible experience, seems at odds with the notion of a universe that may not be real in the classical sense. How can something as immediate as the awareness of self, the ability to think and feel, emerge from a reality that might be based on abstract quantum processes or information rather than matter? One of the challenges in understanding consciousness is that it doesn't fit neatly into traditional physical theories. In classical physics, everything can be explained by the interaction of matter and energy. But consciousness doesn't seem to follow these rules. While we can map the brain's activity using tools like MRI scanners, these scans only show which parts of the brain are active during certain tasks. They don't explain how or why subjective experience, what it feels like to be aware, arises from these physical processes. One idea is that consciousness may arise from quantum processes within the brain. One of the most well-known theories linking quantum mechanics and consciousness is the orchestrated objective reduction theory, or OR, proposed by physicist Roger Penrose and anesthesiologist Stuart Hameroff. According to this theory, consciousness arises from quantum processes that take place in tiny structures within the brain called microtubules. Microtubules are part of the cytoskeleton, the network that gives cells their shape, and Penrose and Hameroff suggest that they might be capable of sustaining quantum states. These quantum states could collapse into definite states, much like particles do when observed, leading to conscious experience. In this view, consciousness is tied to the fundamental, non-physical processes that govern the universe at the quantum level. One of the intriguing aspects of the OR theory is that it posits consciousness as something more than just an emergent property of complex neural networks. Instead, it suggests that consciousness is tied to the deep structure of the universe itself, operating at a level that goes beyond the brain's classical, physical processes. This raises the possibility that consciousness is not simply the result of biochemical reactions in the brain, but is instead connected to the very fabric of reality, whatever that reality may be. This perspective aligns with other theories that propose consciousness is a fundamental aspect of the universe rather than a byproduct of matter. Panpsychism, for instance, is the idea that consciousness is a universal feature of all things, from the smallest particles to the largest structures in the cosmos. In this view, the universe itself could be seen as imbued with consciousness at every level, with human consciousness being just one expression of this universal quality. While this might seem like a radical departure from traditional scientific thinking, it's not entirely out of step with some interpretations of quantum mechanics, which suggest that observers play a key role in shaping reality. Some interpretations of quantum mechanics go even further, suggesting that consciousness and the universe are not separate entities at all, but are instead two sides of the same coin. The idea of quantum monism, for example, proposes that there is only one fundamental thing in the universe, and that thing gives rise to both matter and mind. In this view, consciousness and physical reality are different expressions of the same underlying quantum processes, with consciousness playing an active role in shaping the reality we perceive. There are, of course, many challenges to these ideas. One of the main criticisms of quantum theories of consciousness is that the brain, being a warm, wet, and chaotic environment, is not an ideal setting for quantum processes to take place. Quantum effects typically require extremely low temperatures and isolated conditions, which are hard to imagine inside the human brain. Critics argue that while quantum mechanics may provide a useful metaphor for understanding consciousness, it's unlikely that the brain operates at the quantum level in the way that Penrose and Hameroff propose. Despite these criticisms, research into the potential quantum nature of consciousness continues. One area of interest is the study of quantum coherence in biological systems. Some researchers have found evidence that quantum processes might play a role in certain biological functions, such as photosynthesis, which involves the transfer of energy through quantum states. If quantum coherence can occur in living systems like plants, it's possible that similar processes could take place in the brain, potentially playing a role in consciousness. Where does all this leave us? Physics, philosophy, or fiction? Physics, at its core, is about understanding how the universe works. For centuries, it has provided us with answers that helped explain the world around us, from the motions of planets to the forces that hold atoms together. But in recent decades, particularly as we've delved into the mysteries of quantum mechanics, the answers have become more puzzling. The deeper we go, the more the universe seems to resist simple explanations. In fact, some of the theories that have emerged, such as the idea that reality might be a simulation or that the universe itself doesn't really exist in the way we traditionally think, seem almost too strange to be real. This shift raises the question: has physics moved beyond the realm of empirical science and into something closer to philosophy? After all, many of the questions we're now asking about the nature of existence, the role of consciousness, and whether reality itself is an illusion sound more like the topics you'd expect to hear in a philosophy seminar than a physics lecture. Quantum mechanics, with its uncertainty and probabilistic nature, defies the classical idea of a universe governed by clear and predictable laws. Instead, it presents us with a world that is, at its most fundamental level, indeterminate and unpredictable. This blending of physics and philosophy leads us to a peculiar situation. Are we still doing science when we explore these questions, or have we crossed over into a different realm? Traditionally, science is based on empirical evidence, on experiments and observations that can be repeated and verified. But many of the ideas we've discussed, from the multiverse to the simulation hypothesis, are difficult, if not impossible, to test. We can't easily design an experiment to determine whether we're living in a simulation, or whether the universe exists independently of our observations. This lack of testability is one of the reasons why some critics argue that modern physics, particularly in areas like string theory and quantum mechanics, is veering too far into the abstract. They claim that physics should be grounded in observable phenomena, and that theories that can't be tested risk turning science into speculative philosophy. And yet, these same critics must contend with the fact that many of the most successful theories in physics, such as quantum mechanics, are deeply abstract and counterintuitive. Just because a theory is strange or difficult to test doesn't necessarily mean it's wrong. It's also worth considering the possibility that what we're experiencing is a natural progression in the evolution of scientific thought. In the past, many scientific breakthroughs seemed strange and speculative before they were proven. For example, the idea that the Earth orbits the Sun was once considered radical and untestable. But over time, as our understanding of the universe grew, these ideas became accepted as part of mainstream science. Perhaps the same thing will happen with the strange ideas we're grappling with today. As our technology improves and we develop new ways of testing these theories, we might find that what seems speculative now becomes the foundation of future scientific knowledge. Does this possibility scare you, or does it excite you? Comment down below, and if you enjoyed this video, consider leaving a like and subscribing to the channel. Thanks for watching.